Number 13, describe the end behaviors of the functions f and g. F is this fourth degree polynomial where the initial coefficient is positive. It's basically 1, right? All right, for the end behaviors, because when x has a fourth power, third, second, and first, and the 0th power, they are irrelevant, okay? When x is really, really big or really, really small, the only thing that matters is this. Everything else becomes so much smaller, right? When x is 10, then x to the fourth is at 10,000, where x to the third is only 1,000, right? When x is 1,000,000, then the fourth power of that is huge. So nothing compares to that leading term. Nothing else is important. So just think of that as a fourth power, and the graph is going to go like this. Something would happen here, ups and downs maybe. No, not too many. It could go up maybe 1. Yeah, it could go up and have maybe 2 or maybe 3 of these things. Here, it could have 3 critical points. Well, the points of maximum or minimum, local maximum or minimum, but that's all it could have. It may not have any. It could have 1. It has to have 1. But anyway, so this is what it looks like. No matter what happens here, the end behavior is that as x goes to positive or negative infinity, y will go to infinity in both directions. Okay, so up here and up here in both directions as x goes to the right or to the left. E to the x is very different, okay? And everybody should know what the graph of e to the x looks like. It grows exponentially like this, goes through 0, 1. And so as x approaches negative infinity, y approaches 0. And it never is negative. It always is positive, but does approach 0 rather quickly, actually. As x approaches infinity, y goes to infinity. And in fact, faster and faster to infinity. This is called exponential. Okay, so that's number 13. That's pretty much all you have to say, because the question only asks you to describe the end behaviors. Number 14, evaluate this limit as x approaches 1. This is a polynomial, okay? And you know from the section on the functions or sections on continuity that a polynomial is always continuous at every single point. And because it's continuous, the value of the function is the limit of that function at that point. So as x approaches 1, this function will approach the value of this function at 1, which means that the limit is basically the y value when x is equal to 1, which means just go ahead and substitute 1. Okay, for any continuous function, all you have to do is to substitute the value, plug in other words. All right, so this is 1 minus 3 plus 4 minus 1, and that will just give you positive 1 as your limit. That's probably the easiest type of questions you will see on this test. Number 15, identify and classify each point of discontinuity in each of the functions below. E to the x, the graph is like this. It's always continuous. That's one of the most important facts, by the way, of all of mathematics. E to the x, the exponential function, which is arguably the most important function in mathematics, is continuous at every single point, and it will never become 0, okay? Just keep that in mind. It's continuous everywhere, so there is absolutely no discontinuity, okay? If the function is continuous, then there's no discontinuity, because discontinuity by definition is where the function is not continuous. All right, so nothing else to say here. Now, g of x is slightly more complicated, right? Let's try to factor and see if you can do this. 1 and 3 plus 1 and minus 3 would do that, right? So this will be canceled, and it's equal to 1 over x minus 3 if x is not negative 1. If x is negative 1, then you have 0 over 0, that's undefined, right? So the graph is going to be, so this is that g is undefined if x is -1. Okay, but now this graph. Okay, so that's an interesting thing here. Okay, let me just go ahead and graph this for you. Okay, so it's not necessary that you actually graph this function, but graphing will sort of help you understand what's happening here. Oops, that's not the case. All right, let me do this again. Sorry, so from this equation, okay, what we can see is when x is equal to 3, we have a problem, right? When x is 3, you have something that goes to infinity, positive or negative infinity, depending on which side. And if you analyze the function, you will see that as x approaches 3 from the positive side, like 3.1, 3.11, these numbers, 3.01, these numbers will stay positive, but get very, very small. 1 over a very small positive number goes to infinity. So that's that. If you approach 3 from the negative side, like 2.9999 and so on, these will remain negative, approaching 0. And that means the whole thing will go to negative infinity. Now, when x is -1, right at that point, okay, the function is not defined, but it would be if you just fill in this hole here, right? So what we have is that we have a removable discontinuity at x is equal to -1. It's called removable discontinuity because you can simply remove the discontinuity by plugging in the hole. Okay, I mean, if you just fill this, then you will not have discontinuity. So that discontinuity is easily removable because it's a hole. So the idea of a removable discontinuity is basically when you have a hole. Okay, when things are going to infinity, that's called the infinite discontinuity, and that's happening at x is equal to 3, right? As you can see. Sometimes you have another type called a gap, like when you have something like this, that's a gap discontinuity, but you don't have that in this situation. Okay, so those are the 2 points of discontinuity for this. All right, last one. If you remember the tangent function, this is undefined. And remember what happens is tangent is 0 when x is equal to 0. And it just repeats this kind of thing like that, right? Anytime the angle is corresponding to 90 degrees and -90 degrees, or pi over 2, 3 pi over 2, and so on. Okay, so this is what kind of function discontinuity is this? And of course, this goes to infinity, so it's infinite discontinuity. Discontinuity, or sometimes people call this the discontinuity going to infinity or something, but it's sometimes mostly referred to as the infinite discontinuity at pi over 2 and then plus k pi, right? Because it happens every 180 degrees. So the first one is pi over 2, then go pi, 2 pi, 3 pi, or negative pi, -2 pi, -3 pi, and so on. Okay, so where k is an integer. And so you have in this function infinitely many discontinuities, and all discontinuities are of the type infinite discontinuity. All right, so that is number 15. Let's go to number 16. Okay, so number 16 is all about just 2 functions, natural log of x and e to the x. The question says, sketch the graphs of these 2 functions and explain why or how the graphs demonstrate the fact that they are inverses of each other. And then you have to find the domain and the range. I guess I should make the graph nice. So let me give me a few seconds. All right, so e to the x goes, e to the 0th is 1. So it goes through the point 0, 1, and it never touches, but gets very close to the x-axis, and then it grows exponentially as x goes to infinity, right? So this is e to the x. Now, the natural log of x is the inverse, and if e to the x is y, then log of y is equal to x. So because this point 0, 1 is on this graph, the opposite, the inverse has 1, 0. And certainly natural log of 1 is equal to 0. And it kind of starts to go away from this. And remember, the inverse functions mean that the graphs are symmetric to each other with respect to that line y is equal to x. And then that's because x and y are switched, basically that. Okay, so this is the natural log of y. These two functions are extremely important. So important that you should know like everything about these two functions. Okay, and they are inverses of each other because they are symmetric with respect to WRT in mathematics means with respect to the line y equals x. That is how the inverse functions are illustrated. Okay, so the domain of e to the x is the set of all reals, and the range is, of course, only the positive numbers. Okay, the natural log of x, because these are inverses of each other, the domain is what used to be the range. See that the ln of x is only defined for real numbers, and then the range, well, the y values, it goes to negative infinity, and it slowly goes to positive infinity. So that's the set of all real numbers. That's the range of the natural log of x. All right, as we go to number 17, we will go into next segment of our video.